Before we begin our discussion of reflection and refraction, we first need to understand that there are two ways to represent waves when we draw them on paper. We can use wavefronts or we can use rays. Let's listen up.
Wavefronts and rays. These are two ways of representing a wave. For example, we could have a water wave travelling from left to right like this, and we could represent it by having a line for each peak, for instance. These then would be wavefronts. Alternatively, it might suit us to have an arrow like this showing the direction of travel of the wave. This we call a ray. Here we've got circular waves, for instance the ripples on the surface of a pond, or in 3 dimensions this could represent the waves travelling out from a light bulb. So the lines shown are wavefronts. Alternatively, we could do arrows like this, which would be rays. Rays are always perpendicular to the wavefronts.
The law of reflection. Here we have a diagram of a wave being reflected off a surface. So here you see reflecting surface. It could be a mirror. It could be the surface of a lake. Lots of things reflect light. So here's the incoming wavefront and the incident ray. When light strikes a surface, we say it is incident upon the surface, and when it bounces off the surface, we say it has reflected. So here it's showing both ways of representing the light, both with the wavefronts and with the ray. As it comes in and strikes the glass, let's say it's glass, we can measure the angle that the light is coming in a very certain way. First, we take the surface and we draw a normal to it. Remember, that's a perpendicular line. And then we measure the angle between the ray and the normal. So this right here is called the angle of incidence of the light upon the surface. And then when it reflects off, the same thing. We measure the angle of reflection the same way between the normal and the ray. And so the law of reflection says that the incident angle is equal to the angle of reflection. Most surfaces do not reflect all of the light that is incident upon it. Even your bathroom mirror does not reflect 100% of the light. Some of it is actually absorbed. So when light is incident upon a surface, it could be reflected, it could be absorbed, or it could be transmitted through. So a piece of glass, you tend to think of light passing through it. Glass is transparent. But in actuality, about 4% of the light that strikes a glass surface is reflected. You see this all the time. Here's some examples. Here's a restaurant. As you walk down the street, light is reflecting off the glass. Here inside your living room, perhaps, you see light reflecting off the glass. And sometimes you can't see it, but it's always there. It depends on how bright is the light behind the glass. If there's not a lot of light coming through, it won't drown out the 4% that's being reflected.
So you're hanging out by a window doing what you do. You look out and you can clearly see the buildings, the trees, and the sky. But as it gets darker, something changes. Over time, you begin to see yourself in the window. The window has become a mirror. So why does this happen? Well, your window is most likely made of glass. Glass has some interesting properties. Mainly, it's transparent, which means it can both refract and reflect light. Now, refraction means glass can bend light, but it also means it can allow light to pass through it. Glass also reflects light, meaning the light bounces back in the other direction. For window glass, it's about 8%. You can see this piece of glass both refracting and reflecting this red laser. So what's happening when the sun sets and you turn on a light inside?
So I've set up my camera to be looking out the front window of my house, and I've got here a piece of window pane glass, and I'm going to put it in front of the camera, and I'm sitting behind the camera, and the light from my face is reflecting off the glass, but you can't see it. because the light outside is so bright, it's overpowering, and our eyes adjust to this amount of light and cannot detect the small amount of light reflecting off the glass. But if I block the light from behind, the camera will adjust its light sensitivity just like our eyes do. And now you can see my reflection. I'm sitting behind the camera. This is just my reflection in the glass. And I'm taking now you can't see my reflection. And now you can. Is the amount of light reflecting off the glass changing? No, of course not. It's the same. It's just the sensitivity of our eye can see it better when it's not being drowned out by the light that's behind. And when we let that through, then we can no longer see the reflection. Now I'm outside my house and I'm looking at the window to my living room, and the blinds are open, but you can't see in the window because it's dark inside the house. And the reflection from outside off the glass is much brighter than the light that's coming through from inside. So really all you see is the reflection. Later, we'll wait until it gets dark and we'll turn on the lights on the inside and we'll show you what this looks like from the same vantage point outside, with dark outside and light inside. And now here we are outside. It's the evening now and it's dark outside but light inside, so we can see inside the house very well. No reflection off the glass, or there's very little light outside to reflect off the glass. So we see the light inside the house very well. And here's the window from the inside. It's very light inside, but it's very dark outside. So we see the reflection off the glass very well. Don't we, Leo? Haha. Let's look at a special example of the rear view mirror in your car.
Hey guys, it's Becky from Applewood Ford. I just wanted to show you this kind of cool trick that I just found out. Maybe a lot of you know it, maybe you don't. Let me show you something with your rear view mirror. One sec here. So here's your rear view mirror. You guys ever seen one of these little flicky things on the bottom? I just found out if you grab that, give it a little pull, instant night vision. So you won't have high beams in the back blinding you. Flip it back up for daytime. Day, night, day, night. So I've never heard of that before. Never seen it. So if you guys are looking for a way to not get blinded by high beams at night, there's a little tip for you. Kind of cool.
But have you ever wondered, like, what just happened when I flipped that tab? Well, I'm here to explain it to you. See, what looks like a little piece of flat mirror hanging from your windshield is actually something that's called prismatic wedge. What looks to be flat is actually a angled mirror with a wedge of glass. It's just normal see-through flat glass in front of it at an angle. So when you're driving along and it's normal daylight hours and everything's just typical, when you look into the mirror, you're actually looking right through that angled glass in front, which is now downward, to the mirror and back, and again, everything's normal. You're looking into a mirror. What's there to say? But when it's nighttime and somebody drives up on you with their brights and you flip that tab, the roles are reversed. The mirror and back is now angled upward and the glass is flat to you, which means that about 4% of the light is actually being reflected, which dims the image. Presto!
The law of reflection holds true for curved and uneven surfaces as well. Let's take, for example, this curved surface. How do you measure a normal to a curved surface? Well, of course, we draw a tangent line at the point where the ray is striking the surface, and now the normal is perpendicular to the tangent, and we can measure the incident angle and the reflected angle, and the law of reflection still holds true that the angle of incidence is equal to the angle of reflection. But what if we have a surface that's rough? So this brings up our next two vocabulary words. On a smooth surface, we get a regular reflection like we expect, like a mirror. We can see our reflection. If the rays stay nice and ordered and in line, then we see our reflection. And this regular reflection is also called a specular reflection. If the surface is rough, however, the light rays reflect in all different ways, and now we can no longer see our reflection. We see the object. For example, a piece of paper. If a piece of paper has light striking it, we see the paper, and that is true for anything we see. Light is reflecting back to our eyes. That's how we see it. But when you look at the topography of the paper, here you can see is the scale of my microscope image of this piece of paper. This is 100 microns. So the wavelength of light is from 400 to 700 nanometers, which is very small compared to the topography of the paper. So it gets scattered all over the place, and we get a diffuse reflection. So we see the paper, it's there, but we can't see our reflection in the paper. Over here, however, this is a reflector dish for an antenna which collects radio waves. Radio waves are several meters long. Their wavelength is several meters. So compared to that wavelength, the spaces in between this mesh are very small. And so to radio waves, this dish is very smooth and reflects the radio waves very well. Let's check out this image of a mountain, and we see the reflection of the mountain on the left on very smooth water. We call that a specular reflection, and we can see the image of the mountain. The same mountain, though, on the right, on a windier day, now the surface of the lake is not so smooth compared to the wavelength of light, and we get a diffuse reflection. The next topic we want to discuss is refraction. Refraction is the bending of a wave or changing of its direction. And the reason this occurs is because the speed of the light changes as it enters from one medium to another. The medium is the stuff through which the wave is traveling. So here in this picture is air up here in the white section and water down here in the blue section. And as the wave travels, the bottom part of the wavefront enters the water first and slows down because the speed of light in water is less than in the air, while the top part of the wavefront is still in air and gets ahead of the part in the water, and the result is a change in the direction of the light. Let's look at this animation to understand it better.
One side is slowed down before the other, forcing the wave front to change direction. This bending of light, whether in glass, water, or any other transparent material, is called refraction. Light is refracted closer to the direction perpendicular to the interface whenever it enters a medium that slows it down. This occurs no matter what the direction of incidence.
Here's our setup. I've got my laser right here, which I'll turn on. It will shine into this tank that is filled with water. And then at the bottom of the tank, along the bottom of the tank, I have a mirror so that the light will reflect off the bottom of the tank. Let's turn it on and see what it looks like. Here's the laser up here, and between the laser and the tank of water, we can't see the laser beam because there is nothing that is scattering the light. We need some kind of particles in the air to scatter the light. In the water, I put some mop and glow, which causes the light to scatter, and it allows us to see the beam. But if I put some water droplets in the air, we'll be able to see the laser in the air as it moves into the tank. So here's a freeze frame picture from the video. I sprayed the water droplets in the air so that you can see the incoming laser beam as it enters the water. Then it goes through the water reflects off the mirror at the bottom of the tank, and shines back up and leaves the water, and you can see it over here as well.
Let's start with a very simple experiment. Put a coin in an empty cup. Position yourself in such a way that the coin is not visible. Now slowly add water into the cup. Slowly you will start to see the coin. Observe that the coin is completely visible now. Why do you think this is happening? The coin isn't moving. Rather, it just looks like it has moved up because of a phenomenon known as refraction. Let's take a closer look. We see objects only if light hits them and the rays reflect or refract off them and reach our eyes. In our experiment, the rays of light hit the coin and bounce to our eyes after refraction. When light rays travel from a dense medium to a rare medium, that is from water to air, they are refracted away from the normal at the surface of water. Then, when these refracted light rays enter our eyes, they create the illusion that the coin lying at the bottom of the cup is closer to us than it really is. In reality, we can't observe the zigzag path that the rays of light are taking. Our eyes always perceive rays of light as a straight line. We can draw a line to represent the path of a refracted ray. We can also draw a line to show the path from our eyes back to the refracted object. The point where these rays meet is where the coin appears to be. In reality, the coin is at the bottom of the beaker, but because the light bends when it hits the water, the image of the coin is formed above the actual position of the coin. This is why we are able to see the coin upon pouring water in the cup. The distance from the actual position of the coin in a transparent medium, like water to the surface of water, is called real depth. Can you guess what apparent depth is? The distance from the image of an object in a transparent medium, like water to the surface of water, is called apparent depth.
So when light enters the water, it bends towards the normal. But the opposite happens when light leaves the water. So here, light from a fish travels up to the surface of the water, and once it leaves the water, now it bends away from the normal. We often say that the path of light is reversible. So if it bends towards the normal on the way in following this blue line, then on the way out, it also follows the blue line and bends away from the normal. So these two rays of light coming off the fish, the ray on the right bends away from the normal, the ray on the left bends away from the normal, and our eye that's up here, remember our eyes think that light always travels in a straight line. So we think, our brain says, follow the blue lines, which now in a straight line become the black dotted lines, and where they meet is where we will see the fish. And that is the apparent depth of the fish now, which is less than its real depth. And here we can see very obviously with this ruler, when we look under the water surface, we see that the centimeter marks are much closer together. So this distance looks less than 5 centimeters, when actually we can see that it is a little more than 5 centimeters. So we've said that light bends away from the normal when it leaves the glass and goes into the air, or leaves the water and goes into the air. Anytime it goes from the slower medium to the faster medium, the light will bend away from the normal. So something very special happens at a certain angle, and we're going to demonstrate that right here. Here we have a piece of glass and a light source, and we're going to move the light source around this curved edge of the glass. And the light is always entering the glass perpendicularly to the tangent. So you can see there's no refraction happening here. But when it leaves the glass, we see it bends away from the normal. Right here is my angle of refraction, and right here is my angle of incidence, and my angle of refraction is larger. If we keep going, you're going to notice that this ray of light is going to be right along the edge of the glass. And you can see already we're starting to get some internal reflection. But once we reach, now I'm going to pause it there, that is the critical angle. That's where the refracted ray was right along this edge of the glass. Now all of the light is reflecting off the surface of the glass, and you can see now it's obeying the law of reflection. And if we go beyond the critical angle, the law of reflection still holds, and the light remains inside the glass. Of course, over here, it's incident upon the glass-air interface perpendicularly, and so it leaves with no refraction. But right here is total internal reflection. This is an extremely important concept when it comes to fiber optic cables and how our society functions today with the internet.
Have you ever thought about how you get emails or any other information from any corner of the world within a blink of an eye? This has been made possible by a network of cables, which are laid under the ground and below the ocean. The cables, which carry most of the world's data, are optical fiber cables. They are also used in medical equipment. Let's learn how optical fiber cables work and how they have revolutionized the world around us. Optical fiber cable is made up of thousands of fiber strands, and a single fiber strand is as thin as a human hair. Optical fibers carry information in the form of light. Let's first learn some fundamental behaviors of light to understand the workings of optical fibers. The speed of light changes when it passes through a medium, and this change in speed is expressed by the refractive index. This variation in the speed of the light leads to another interesting phenomenon: refraction. To understand what it is, let us carry out an interesting experiment. In this experiment, light passes through a prism. You can see that at the interface, the light gets bent instead of going straight. This phenomenon is known as refraction. Refraction occurs when light passes from a medium with one refractive index to one with another refractive index. The light bends towards the interface when it goes from a medium of high to one of low refractive indices. Refraction is the reason why a pencil looks bent in a glass of water. This simple refraction technique is effectively used in optical fibers. Now, let's make this experiment a hypothetical one. Using some dopants, we are able to increase the refractive index of the glass in real time. As we increase the refractive index, the light will bend more and more towards the surface. After a time, you can see that the light will pass through the surface of the glass. If we increase the refractive index further, the light will suddenly come back to the first medium as a pure reflection. This is called total internal reflection. The total internal reflection is possible if we increase the incident angle rather than increasing the refractive index. In this case, at a certain angle called the critical angle, the light will come back to the first medium. This phenomenon of total internal reflection is used in optical fiber cables to transmit the light.